Okay, so for the first one here, adding 14.3 inches to 9.88 inches is going to give us 24.18 inches. Now we have to round that appropriately. In fact, I'm going to do this quick, move it out of the way. Our first number here, 14.3, remember addition and subtraction worry about precision, which is the place value of that smallest significant digit. This is significant, this is precise to the tenth, so that's 0.1. This is precise to the hundredth, that's 0.01. Well, we are worried about the less precise number, which is the tenth. So our answer here is rounded to the tenth. So that 8 says we round that up to 24.2 inches to the correct significant digits. Number 2, we first have to multiply the 7.4 inches times 0.365 inches, giving us 2.701 inches squared. So now we look at for multiplication and division, we preserve accuracy, which is the number of significant digits. This number here has 2 significant digits. This one has 3 significant digits, which means our answer has to be rounded to just 2 significant digits. So 1, 2, we're going to round it there. That rounds 2.7 square inches. Any questions on the first two? Number 3, we have to divide 27.3 divided by 2.7. We get 10.111111. That'll be pounds per square inch. Again, this is division, just like multiplication. We count the number of significant digits. This has 3 significant digits. It has 2 significant digits. So our answer has to be rounded to 2 significant digits. So we start at the beginning, we count 1, 2. We're going to have to round there, which is going to be 10. But we can't write it like this because the way it's written right there only has 1 significant digit. We have to indicate that 0 is a significant digit. Number 4, subtraction. 274 inches minus 24.2 inches is 249.8 inches. Now remember, we look at place value. Addition and subtraction, it's about precision, which is the place value of that last significant digit. This is the ones place, that's the 1 inch place. This is the tenths, 0.1 inch. So the one that's less precise is the 1 inch. So we round to the nearest 1 inch here. And that 8 says we round up to 250. Once again, though, that ones digit is significant. So we once again have to indicate it by putting a line over that 0, that 0 is a significant digit. How many of you had all 4 of those right? Any questions on those? I realize it's almost like a foreign language because this is not the way you're used to thinking about doing math. But as I mentioned on Friday, there is a lot of importance there. If you're going to be looking at design drawings and calculations made by engineers and designers, you will see them rounding using significant those tolerance buildups. So it's important that you at least understand why they've rounded that way. Not necessarily that you're actually able to perform the calculations to the correct significant digits yourself, but at least be able to understand why others have rounded the way they have. Because there are some of these calculations, it looks like you've lost a considerable amount of information by rounding it off, but you haven't. What you've rounded off is really kind of a wash in the error of your measurements anyway. We're only making sure that we don't report something that's more precise than what we actually meant. Like I said, we will have that on a quiz tomorrow. And then we will have a few problems on a test, but I will make sure that before the test hits, we review that again so that you are ready for them. It's not something that I expect you to have on the top of your head ready to go every time I ask for it. All right, so today we're staying on a related topic, just a little bit different way of looking at it. We're going to look at errors. Errors can be created by a couple of different things. One source of error is human error. Human error is very difficult to quantify. Because if you do something wrong when you take a measurement, the only way you're ever going to check it if somebody else comes back and double checks your measurement. Well, that second person double checking your measurement also is going to have an error. So the actual human error, or literally the mistake being made, is tough to quantify. Then there are errors in process. For you guys, this is actually a big thing in machining and manufacturing. Error in process is just the ability of your machine. If you're going to drill a hole in an object, when that drill hits the surface, there is a natural tendency as that drill is spinning, when the tip hits the surface, for that drill to slightly deflect to one direction or another. So even if you have that part lined up perfectly when the drill comes down, it's not going to drill exactly the same spot in every part because of that tip of the drill hitting and that the tendency to slightly deflect to one side or another. The same is the true for cutting. When you cut, the same thing is going to happen. When the saw hits, that blade can slightly deflect and throw it slightly off. Mills are the same way. Everything we do has some sort of an error in process with it. This is what we use statistical process control for. There used to be a little bit of SPC built into some of your shop courses. When we cut it back to 1 year, not so much. Mr. Becker may mention a little bit of that yet in your stuff. If we get time in the spring, at the end of the spring semester, we will touch on statistical process control a little bit. It's a little bit of a dry topic, and we rush through it in just a few days for whatever days we have left, which makes it even more exciting. But it is a very important concept to have a little bit of an understanding of. And then, of course, we have built-in errors in the device. And this is our measurement errors and stuff where, the precision is built in by the smallest division. And that's as close as it can get. So they're called precision limits. So this would be when you're setting up your process, setting up your machine. If you're setting up a jig to put the part up against to cut it, or to put the part up against to drill it, that jig has to be set up using some sort of measuring device. Well, there's limits in the precision of that measuring device that are going to limit how closely you can actually set that jig up. So I'm going to turn off the engineer in me and stop talking about errors, or the sources of error, because I could go on for a couple hours on that. And just get into turn back on the mathematician and just talk about the types of errors. Errors are, I won't say bad, errors are undesirable, but they are there. There's an error in everything we do. And so we need to understand what type of error applies to what we're doing. Mathematically speaking, there are really only two types of errors. There's something called an absolute error, which is just plain the difference between the desired value, if you're trying to build something, cut it or whatever, and the actual value. You want it to be exactly 3 inches long. You cut it, as we mentioned, your saw deflects a little bit. It ends up being 3.02 inches long. You had 0.02 of an inch of absolute error. Or it can be the difference between the measured value and the actual value. We go to measure it, but remember, all measuring devices have a built-in error, so we have to round to the smallest unit of the device. This can be predicted. With knowledge of the measuring device. We know the degree of precision of the measuring device. We know that built-in error of the measuring device. If we use it correctly, if we take out the human error, we know what the maximum measurement error should be. So if we have an object that is 2 5/16 inches, and we measure it at 2 1/4 inches, our absolute error is the difference between those. Now notice I said measured value minus actual value, but I really just want how far it is between. I don't care which one's bigger. So I'm going to take the larger one, 2 5/16 inches, minus the smaller one. Error is not directional. It's just the difference between the two sizes. So it is a 1/16 of an inch is our absolute error. Then we have relative error. Relative error is just that. It's the size of the error relative to the size of the part. So relative error is the absolute error divided by the actual value. So for our example up here, we had an absolute error of a 1/16 of an inch divided by our actual value of 2 5/16 inches, give us 0.027 is our relative error. Notice there are no units on that. The units should divide out. Inches divided by inches cancel out to give us a relative error. Now, depending on the textbook that you're using, some textbooks treat this third piece as a different type of error. Really, it isn't. It's a different form of writing the relative error. And it's called percent error. The percent error is simply the relative error converted to a percent. So this is in decimal or rate form, the 0.027. To convert it to a percent, we multiply by 100 or just move the decimal point over 2 spots. That's a 2.7% error. A lot of times we make that conversion into a percent error just because it's easier for us to understand what 2.7% means than 0.027. Just because our brain's a little bit more hardwired, hey, that's more than 1% error, but less than 5. We have an idea of how big that is. Where 0.027 looks like a really tiny number, but it's not. That's actually a significant error. That's more than 1% error. We really probably aren't going to be happy with that. So let's look at this error in terms of measurement. Assuming we report the measurement correctly, let's look at 2 measurements here. I want 2.3 inches and then 26.2 inches. Both of these measuring devices have a degree of precision of 0.1 inch. Because they both go to the 10th of an inch. Which means their possible error, their measurement error, is plus or minus 0.05 inches for both measurements. That is what's considered to be the absolute error. Well, why do we say that's the absolute error? It might be less than that. Yes, it might be less than that. But if we know the actual value of something, there's no reason to measure it. We are measuring it because we don't know the length of that object. So because we don't know the actual length of the object, we don't have anything to subtract to get that absolute error. So we like we mentioned on Friday, we do worst case scenario. The worst case scenario, if we use that measuring device correctly, is that our absolute error is the maximum possible error in the measuring device, which is the plus or minus 0.05 inches for both of these. The relative error, however, is going to be different for each of them. Now, we don't know the actual size of each of those pieces, but we know it's pretty darn close to whatever we measured. Hopefully we didn't screw it up too badly. So the relative error can be found by taking our absolute error, or the maximum error of our measurement, 0.05, and dividing by the measured value. We can put that in there in place of the actual measurement, because we know the actual measurement should be really close to that. The 0.05 divided by 2.3 gives us 0.02174. Now, if I convert that to a percent, that's 2.174%. More than 2% is probably not acceptable. On the other side over here, we've got the 0.05 inches as our error over 26.2 inches. .00191. If I convert that to a percent error, it's 0.191%. Less than 1/4%. That's probably acceptable. So the point of this example here is that measuring device that's precise to 1/10 of an inch gives us, even though it gives us a plus or minus 0.05 as an absolute error in both cases, in this case gives us an acceptable relative error or percent error. Whereas over here, that is not over 2% is not an acceptable relative error or percent error. Why is there a difference? Well, because what we were measuring over here was larger to begin with. So one of the things in measurement quality control is you have to match the precision of your measuring device to the size of your object. If I'm measuring something that's 26 plus inches, having a measuring device that only goes to the 1/10 of an inch is okay, because it's going to give me, a relative error that's less than 0.25%. But if I'm measuring something that's only a few inches in size, a measuring device that's only precise to the 1/10 of an inch is not okay. It's going to give me too big of a relative error. So I need to find something more precise for measuring that object. Well, along with that discussion of errors comes this discussion from blueprint reading or whatever task you're looking at. What does that label there mean?
The length is 400 thou. It's got to be plus or minus 5 thou.
Perfect. We want the length to be 400 thousandths. That's called the desired value. Sometimes called the ideal value, because in an ideal world, that's the size we want it to be, is exactly 400 thousandths of an inch. Some people, the plus or minus 5 thousandths, like you said, we can be off a little bit smaller, a little bit bigger by 5 thousandths of an inch. A lot of people incorrectly call that a tolerance. It's actually an allowance. I'm not going to be real strict on language in here, but I just want to point out what the proper terms are. This is implying a range. Just like our measurements did. And that range, of course, will be the 400 thousandths minus the 5 thousandths. So the 0.395 inches to the 400 thousandths plus the 5 thousandths. 0.405 inches. That is our implied range from that measurement that's given, from that label. The tolerance is the difference between those two measurements. That's giving you a tolerance of 10 thousandths of an inch. Now again, a lot of people look at this and they just say that's 400 thousandths with a tolerance of plus or minus 5 thousandths. Most people understand what you're saying when you say that, but be aware that when you hear the word it has 10 thousandths of an inch of tolerance, that if they're using the term properly, they're talking about the range between the minimum and the maximum size, allowable sizes for that part. This, by the way, is what's referred to as an absolute allowance. Five thousandths of an inch, plus or minus, period. It doesn't depend on what the desired value is. Although we can have something like this, where this might be labeled 0.320 inches plus or minus 0.5%. This, of course, is a relative allowance. Because the size of the actual allowance depends on the size of the desired value. So to find an absolute allowance from this, we have to set up 0.5% is 0.5 out of 100. Our desired value of 0.320 goes on bottom. And we will cross multiply and divide. 0.5 times 0.320 is 0.160. Divided by 100 is 0.0016. So the absolute allowance there is 0.320 inches plus or minus 0.0016 inches. I'm going to trust that you guys can make that conversion from one to the other. We do need to understand a little bit about what this means and why we might use it. What does that mean?
Can't be bigger than 0.65.
Perfect.
Small.
Perfect. We want it to be 650 thousandths, 0.65 inches. But in a perfect world, an ideal world, that's what we want, we would desire it to be. But it cannot be larger, but it can be smaller. Now this is going to give us an allowable range of 0.65 minus the 10 thousandths, so that's 0.640, to 0.65 plus nothing, which is just 0.65. Well, that is the exact same range we would get if we had listed this as 0.645 inches plus or minus 5 thousandths. It would give us that exact same range. So why list it like this instead of like this? Well, this, by the way, is called a unilateral tolerance or unilateral allowance, depending on how you want to specify it. This is called bilateral, meaning it goes in both directions. Unilateral, one direction. Well, there is actually a good reason to do it this way instead of this way. And that is because we're looking at what we actually desire. This is telling whoever is making the part that we really want it to be 645 thousandths. Get as close to that as you can. Be off by no more than 5 thousandths either direction. This is telling whoever's making it that we really want to be 650 thousandths. So then it comes down to the process. Let's say, I won't get too technical with it, but it's a term called process capability. Let's say that you're looking at a 95% quality, so you want less than 5% of your parts to be outside of your allowance, outside your tolerance. So let's say that your process is capable of producing 95% of the parts to within 2 thousandths of an inch. If the design drawing or the blueprint is listed like this, I'm going to set up my machine to 645 thousandths of an inch. Let it be off by plus or minus 2 thousandths, I'm well within that range. But if my tolerance is listed like this as the unilateral tolerance, I'm going to set up my machine 648 thousandths of an inch. Maybe if I want to play it safe, I might set it up at 647 thousandths of an inch. Even though both of them give the same range, they're giving the machinist different information. This is saying, hey, stay in that range still, but if your process is capable, shoot towards the higher end of the range, towards the 650. Where this is saying shoot towards the middle of the range and stay within it. I want to talk a little bit about special fits. We have two types of fits. We have an interference fit and a clearance fit. An interference fit is intentionally designed so that two parts bind. If there's a pin that's supposed to go into a hole, the hole is purposely made a little too small so that once you get the pin in there, you have to force the pin in, and once it's in there, it's going to stay. That's a pressure fit, in other words. A clearance fit purposely leaves some space. So again, if we're looking at a pin going into the hole is purposely created too large so that there's the little extra room. When the pin goes in, it slides in freely and comes out without binding at all, so that those parts can very easily work together. So let's look at interference and clearance fits here. I'm going to take frost plug here. Going into the block of a car. Both measurements have 4/1000ths of an inch of allowance. For the plug, what is the minimum size of the plug over here? If we subtract the 4/1000ths from the 750, we get what?
746.
746. What's the maximum size of that plug?
754.
754. Good. For the hole, what's the minimum size?
736.
736. Maximum?
744.
744. Now, when we look at our interference, our minimum interference is when the plug is small and the hole is large. What's the difference there? 2/1000ths. Good. Our maximum interference is when the plug is large and the hole is small. What's that difference? 18/1000ths of an inch. You think about 4/1000ths of an inch seems pretty small. It is less than 1% for both of these measurements. It's actually about 0.6% for both of these measurements. But when two parts have to work together, 2/1000ths of an inch of interference, it might hold in place, but it's not going to stand up to a lot of tension if it's being pulled on. 18/1000ths of an inch of interference, it might be hard to press that into the hole. Might be a little too much. So one of the things we have to consider when designing and manufacturing parts is what they're going to be working with and why how the tolerances are going to affect each other, the allowances are going to affect each other. This is where you get into cars, the problems with aftermarket parts. Aftermarket parts, in many cases, are not designed off of the original design drawings of the part. They actually purchase 100 of the actual manufacturer's parts, measure them up, and they reverse engineer their design drawings off of the actual parts. Well, there's errors in the building of those parts, so there might be errors in their design drawings, or their allowances are going to be slightly larger. And so because of that, their interference fits and clearance fits have a lot more issues because they have higher tolerances. And you can see here, 4 thousandths of an inch seems like a small tolerance, but it can give us a tremendous range in our interference. Clearance works the same way. Let's go off like a locator pin. On heavy equipment, if you're going to install a starter, an alternator, anything like that, they a lot of times use locator pins. Those locator pins are made so you can easily slide the piece on there. It holds it in place where you get it lined up for the bolts to go through to hold it in place permanently. So let's say we have a pin that's 250 thousandths plus or minus 3 thousandths, and a hole here that is 250, now let's go 260 thousandths plus or minus 3 thousandths again. So we have our pin and our hole again. What is the minimum size of our pin?
240.
247, good. Maximum size? 253, yes. How about for the hole? Minimum size? 260 minus 3, 257. Maximum size, 263. Now we are looking for clearance. Our minimum clearance is when the pin is large and the hole is small. What's the difference there? Only 4 thousandths of an inch difference. Our maximum clearance is when the pin is small and the hole is large. If I look at the difference there, that's 16 thousandths of an inch. This one's not so bad. 4 thousandths of an inch of clearance might be a little tight. If you have any nicks or scratches on the pin or any gunk in the hole, it might bind up a little bit on you, but that shouldn't be too bad. 16 thousandths isn't enough that it's going to get really sloppy and loose on you. But you can still see how those allowances build up. And that is a pretty healthy sized range between the minimum and maximum clearance. So even though, like we said, the allowance may seem small enough on a single part, when those parts start interacting together, the combined allowance, or it's called tolerance buildup or error buildup, can create some very large differences. Okay, for homework. This is all in the big book. Page 272, this is exercise 7-9, 7 through 17, the odd. Page 273, exercise 7-10, Also 7 through 17 the odd. And finally, page 276, exercise 7-11. 7 through 15 the odd. Also out there, it will be posted later today. There will be a quiz. It actually is, it won't technically be assigned until tomorrow, but if you're doing well on this stuff, you just all work ahead. That will be due by noon on Thursday. What will that be? September 17th. I only left you guys with a couple of minutes here, so I won't make you sit and work. If you want to get cleaned up and head out, we will. That's okay with me.